All right, these are some more problems from section 4.3, and this is number 16. And all we wanted to do here was find the points of inflection, find all points of inflection of the function. So we have to take the second derivative. So in order to do that, first of all, we've got to take the first derivative. So instead of writing it like this, I just multiplied it out. I didn't want to use the product rule, just multiplied it as a polynomial. So it's going to be 4x to the third minus x to the fourth. Then I take my derivative, which is, 12x squared minus 4x to the third. Then the second derivative would be 24x minus 12x squared. This is not undefined. It's a polynomial, but it's equal to 0. So I set it equal to 0, or it can be 0. And I factor out the 12x. So when x is 0 or when x is 2, this will be 0. So those will be my critical points. And just put it in here. These are my 0, 2. This is my second derivative. I'm sorry, not my critical points, my possible points of inflection. Pardon me. This is the second derivative, possible points of inflection. They are critical points, but in the second derivative vein. And then I tried -1 in the original function. And -1, I got negative. If you put -1 in here, you'll get, -24, -12 definitely, because -1's positive. Sorry. Yeah, and that's negative, so negative. And then if you put 1 in here, you get 24 minus 12 is positive. And then if you put 3 in here, you get, this is going to be 72, and this is going to be 9, and -12 times 9 is way bigger than 72. I think it's 108, so that's negative. Okay. So I found the y values for 2. 0 is easy, because if I put 0 in here, I get 0. So 1 point was 0, 0. One of the points of inflection was 0, 0, because concavity does change. This is concave down, concave up, concave down, so concavity does change at these points. So they're points of inflection. Then if I put 2 in the original function, and that would be x cubed minus 4 minus x, so 2 cubed times 4 minus, x cubed times 4 minus x, 2 cubed times 4 minus 2, which is 8 times 2 is 16. So these are the points. So 0, 0, and 2, 16 are points of inflection because concavity changes there. So I think that's pretty similar to what we did previously. So this is just kind of some review problems. Hope that makes sense. And then we have a motion problem again. We want to describe the motion of the particle. First of all, this is number 28, so we want to find, if this was the position function, we want to find the velocity function and the acceleration function, then we want to describe the motion. This is a little bit different, you'll see, than some of the other ones we've done. So first of all, if I take the derivative of the position function, I'll find the velocity function. So that's just going to be 6t minus 6t squared. Then if I take the derivative of the velocity function, I'll get the acceleration function, so that's going to be 6 minus 12t. So those are the two A and B parts. And then the C part, we want to describe the motion. So where do I start? Well, I start when t is 0, so let's find my position at t equals 0, and that's just 0. Well, what's my initial velocity? And this is where it's a little interesting, because the initial velocity is also 0. So I'm sitting there. I have no initial velocity, so I'm not being pushed or pulled either direction by just a force like a rocket or anything to give me velocity, but I am being pulled by an acceleration because the acceleration at 0 is positive 6. So that means I'm going to start at 0, and I have no initial velocity, but then all of a sudden I'm being pulled or attracted to the right because my acceleration is positive. Now I'm going to keep going there until my velocity stops. So when is the velocity equal to 0? Well, it's equal to 0 at two places. First of all, I set the velocity equal to 0. I factor out a 6t, and it's equal, the velocity is 0 either at time equals 0, well, that was my initial time, or t equals 1. So I'm going to be pulled by this acceleration, this positive acceleration, till I stop. And the reason why I'm going to stop is because the acceleration is varying with time. Okay, the acceleration, as t increases, the acceleration goes from positive to negative because it starts to getting bigger and bigger, and that's a negative factor, a negative term, so that's going to outweigh the positive term. So as I'm going, my acceleration starts out at 6 and slowing down until right there, then it's going to go negative on me. So I'm going to stop at t equals 1. And at t equals 1, what's going to happen if I put 1 in for my position to find out where I'm at when t equals 1, because that's when I stop. That's when I stop. Where I stop, I put this into the original function, and then I have 3 times 3 minus 2. Looks like 3 times 2, 3 minus 2. So that's 3 times 1 minus 2 times 1, so 3 minus 2, which is 1. So my position is 1. And when I stop there, what am I going to do? Well, let's see what the acceleration is there at 1. So I put 1 in for the acceleration, and right here my acceleration is negative 6. So this is going to slow me down. So somewhere in here the acceleration is going to turn from positive to negative, and it's going to start slowing down until I stop, and then it's going to pull me that way. Because that right there, the acceleration is to the left, so it's going to pull me to the left. So we can say, to summarize it, we can say at t equals 0, the particle begins at position 0. So that's my initial time and position, and moves to the right because of this acceleration factor. At t equals 1, the particle stops at position 1, and then moves left thereafter. So again, you have to look at your initial position, initial velocity, your acceleration, and the acceleration was the thing that kind of determined what was going on. That was all of your motivation of motion. Okay, so I hope that makes sense.